Good afternoon. I guess good evening. Technically, because it's dark. How's everyone? I'll give it a couple more minutes to see, to let people come in. You can see where I'm starting. This is in Unit 4. The page in your notes, let me see which page that is. So this is the beginning of the assignment, the practice assignment, where I offer you the answers. I provide the answers. So when we left off, I said work ahead, try the exercises in the notes, read the notes, try the online quizzes, and you might have felt, if you did try the online quizzes, that you were underprepared because I haven't really completed Unit 4. So I want to talk about the last few important things. Oh wait, I still need to do that, don't I? Sorry, I'm just scrolling through. Okay, before I do this, I need to talk about distributions. Okay, so let's start here. So I take some time to, can you hear me? I take some time to go through the different kinds of distributions you can expect to see in this class. So there's no surprises, or little surprise. Removes a lot of the anxiety, right? So this is what you can expect to see, these kinds of distributions. So I've divided them up between discrete and continuous distributions. A discrete distribution, as we saw last class, is a distribution where I can list the possible outcomes. So here are the possible outcomes for this one. This variable is the month that our robot arm will break down. Okay, so it was, okay, so that's from this example. So it could break down, we have information only on 4 possible outcomes. It can break down in 1 month, 2 months, 3 months, or 4th month. By the 1st month, it has a 5% chance of breaking down. By the 2nd month, a 25% chance. By the 3rd month, it's 50%, and the 4th month, that leaves 20%, for a total of 100%. Then, so this is analogous to your standard normal table, although there's hundreds of probabilities there. For a discrete distribution, you only see them listed here with their probabilities that still have to sum cumulatively to 1. We can graph this, and I talked to you about graphing this distribution, a distribution like this. It just turns out that they're spikes. So where I plot the probability here of the variable taking on the value little x, okay, we always use little x for the values. For the chance that it takes on 1 is 5%. Oh, you can't see that. Let me make this fit. Let me make this fit better. There you go. So the chance that it breaks down in 1 month is 5%, 2 is 25%, 3 is 50%, and 4 is 20%. And if I was to stack these spikes, it would be a total of 1. Okay, so again, it's analogous to what you see when I make the continuous distribution graph for a standard normal distribution, but it's different because this is discrete, so you should think about that. Another type of discrete distribution that you should be familiar with, that we're going to spend actually 1 unit dedicated to it, or 1 section of a unit, unit 5, is the binomial distribution. The binomial distribution is a special discrete distribution that we formalize in the next unit. It looks like a discrete distribution like the one we just saw, but in fact, there's a formula, or there's a pattern that's expressed in a formula to calculating those outcomes, the probability of those outcomes. So for example, a binomial distribution is something you've already seen before. Remember the variable number of tails and 4 flips. The possible outcomes for 4 flips of a coin is you could have 0 turn up to be tails, 1, 2, 3, or 4. And these are their probabilities, and you see a sort of a pattern, right? 0 and 4 have the same probability, 1 and 3, but 2 is in the middle. So is that always visible in a binomial distribution? Well, no, but anyway, let me show you the graph first. This is the graph for the binomial. You see the spikes, and it appears symmetric. So our binomial distribution is always symmetric. Well, in this case, if p equals 50%, it will turn out to be symmetric. There's another special case where it turns out to be symmetric, and we'll discuss that, as I said, in the next unit. Okay, so it doesn't have to be symmetric. So what is special about the binomial? Why does it have a special name? Why does it have a special formula or a pattern? And what is that pattern? There are 3 criteria that will establish that your variable is a binomial random variable. It can be expressed as the number of successes out of n independent trials. That sounds very technical, but you'll see that's pretty much what it's going to say every time. If you can identify these 3 criteria and you can express x, the variable, as the number of successes out of n independent trials, then what you do have is a binomial random variable. So what are the criteria? First, when you're observing, what you're looking for, so think about it as you're sampling and you're looking for something. If the thing that you're looking for we'll call a success, so that's what a success is. So you're sampling and you're looking to see how many couples got married in June. Okay, so you interview couples and you find out how many couples were married in the month of June, and that is the success. That's what we're looking for, that they were married in the month of June. A failure would be not in the month of June. The chance that that your success occurs should be known. We give it a special symbol, P. That probability should be known, and it should be the same for each of the trials. So for every couple that we ask, we should have an idea from couple to couple to couple, what's the chance that they got married in June. And it doesn't change from couple to couple. So those are independent. Remember, when probabilities don't change in observing sequential events, then we call those events independent. Finally, the number of trials, in our case the number of couples, is known to be a finite number. So I couldn't just say, just keep on asking as many couples as you want. It would have to be fixed, finite, known number of trials. Okay, so if you have this information, P is the known probability of finding what you're looking for, and N is the number of times you look for it. And what you're looking for could just be one of two things, success or failure. What you have is a variable known as a binomial random variable. So we're going to spend more time on that next week. But for now, you should know that, okay? And what this helps us do, just like if we know a variable or we know a characteristic comes from a distribution that is normal, then we can make predictions. And the similar thing, if we know a variable is binomial and a characteristic can be described with a binomial as a binomial random variable, then we can make predictions. Same thing. So just an example here. With N, the number of independent trials, and P, the probability of success, we can simply use a formula to determine the probability of events associated with X. We would write X is binomially distributed. So this means, remember, distributed as, my handwriting is messy. As binomial with, what are these? These are parameters. We call these parameters. They're the characteristics of the variable. They're characteristics of the variable that help determine the pattern for the variable, or the probability distribution, which we can use for estimation and making predictions about possible outcomes. So just like when we talked about the binomial, the normal, if X was normal, we needed mu and sigma to draw it. Remember? So similarly, we need N and P to describe the binomial distribution and then make predictions. Okay? So, for example, I could ask a question like, find the probability of seeing more than 5 people holding an umbrella on a rainy day. Why would I want to do that? Maybe we want to be sure that we have at the front of a business or in a mall, we want to have enough bags for the umbrellas. If you've ever seen the bags in Nordstrom, right, that you can put your umbrella in when you walk in to avoid wetting the floor. So we want to see if we need more than 5 bags at any given time. So we're going to see if out of 100 people, we're going to look at 100 different people and see if they have an umbrella or not. So what would be the probability of seeing more than 5? That's what I want to find out. Now X is the variable that is defined as the number of people that carry an umbrella on a rainy day out of 100. So remember, this is what we just plug these in, right? Number of people that carry an umbrella on a rainy day out of 100. Those are the key things. All that's missing is, so the n is 100, because that's how many people we're going to observe. Those are the independent trials. And p is the chance of a person holding an umbrella. Now, I might not know it, but then if I don't know it, then this is not a binomial problem. If I know it, I can set it up as a binomial problem, where the success is observing an umbrella, failure would be not observing an umbrella. So that's the first criteria. The second criteria is knowing the probability of success, which we know as 10%. So P is known to be 10%. And finally, that there are independent trials. That means from person to person, the chance stays the same that the next person is going to have a 10% chance of holding an umbrella. If that's true, then there's independent trials, and there's 100 of them. So in this case, we write x is 100 is distributed binomial with parameters 100 and p. So 100 is the n, and p is 10%. Okay. Now I never answered the initial question. The question is find the probability that more than 5 people are holding an umbrella. We're going to talk about that in Unit 5. All I want you now to be able to do is to be able to determine if you have a binomial distribution or not, given a problem or setting or scenario. So then I mention here some other distributions that you might have heard of. I'm not going to test you on these. I think I have some exercises just for practice. If you bought the textbook, there's some more exercises in there. But I'll mention them again in Unit 5. So these are other kinds of distributions, just to contrast with the binomial distribution. There's also Poisson distribution and hybrid geometric distribution. There's several distributions that characterize phenomena. For waiting in lines or lineups, for queuing, Poisson distributions are often used. For selecting cards out of a deck, so for making predictions in a casino, hypergeometric distribution could be used. Okay? So those are particular distributions for particular settings. They both use P and N, but they're used differently in these other distributions. So I'm not going to test you on those formally. I just want you to be aware of them, and maybe some of you have heard of them before. What I really want you to know well is the binomial distribution. So here's an example. Take a moment, read through it, and see if you can tell me whether this setting is a binomial setting. I'll give you 5 minutes to read through that and try that. Okay, so did you have a chance to read that? So this is a test for ESP. ESP is extrasensory perception or telepathy. So we're going to see if someone can read minds. And the experimenter is going to look at cards that are hidden from the subject of the experiment. Each card contains either a star, a circle, a wavy line, or a square. An experimenter looks at each of the 100 cards in turn, and the subject tries to read the experimenter's mind and name the shape on each card. Okay, so that's the experiment. It turns out we're going to specify the rule that if a subject gets at least 50 cards correct, they will be demonstrating that they have ESP. So we want to know what the probability of having ESP is. So what we want to know is what's the probability of guessing more than 50 correct. So what's X? X is I'm going to write it, well, it's here. It's the number of correct guesses, I should add in, out of 100 trials, or tries, right? Let me erase this. Let me do that again. And then with that, what's the P? Sorry, what's the success? So you can do this with every exercise that I ask you for the binomial to check if it's a binomial. You work through first defining X, then the success, then the P, and the N. I do them in a different order, but that's what I would do. So what would a success be? A success would be, well, if you remember back when I defined X as the number of successes, that means correct guess is a success. And a failure is just a wrong guess. P is the chance that a person will correctly guess one card. So we can just say an average person who doesn't really have special powers. Okay, let's just say this is it for the average person. What's the chance that they would guess correctly? Well, they're just guessing, right? So, and there's four possible outcomes. So we know if he's just guessing, each one has a chance of 1/4 of being right. So 1/4 or 0.25. Eliana is asking about this, the initial question about the 50. If it says greater than 50, then it's greater than 50. If it says at least 50, yeah, I would put equals. Let's put equals on because it says at least. Right. Thank you. So back to this. So N, what's the number of independent trials? We're going to try this 100 times. Okay. So it is a binomial setup. So X is binomial, N is 0.25. Sorry,
I said n. N is 100 and P is 0.25 or 1/4. And again, we cannot answer the question, but you'll see in the notes that I'm going to use this example again, and we're actually going to answer that later on. Okay? Questions? So far we've talked about discrete distributions in general. Then we talked about ones with patterns. One is the binomial that we're going to focus on. There are also Poisson distributions, hypergeometric distributions. Those I'm not going to test you on, but I just want you to be aware of them, that there's other types of distributions. I don't know exactly how many have been formalized in statistics literature, but I think I could say, I don't know if I want to say 100, but there are formalized distributions in the order of about 100 different kinds. Okay? I should probably check that, but if I think about it, I realize there's a lot. Okay, so then there are the greater group. So I said A, I used A for discrete distributions and then B for continuous distributions. So the continuous distributions that we focus on in this class, I said there's three main types. There are the uniform distributions, the normal distributions, and the t-distribution. Okay? The uniform distribution looks like a rectangle. And I did talk about this with you before. All you need to describe the distribution, remember when I say that, I'm referring to characteristics that help us visualize, draw, and make predictions, right? So all you need to be able to draw this are the lower and upper bounds. So I use lower and upper. In some textbooks they use A and B. So there could be infinitely many kinds of uniform distributions, but the point is that formally this is how we depict it, right? Lower and upper bounds. So for this one, here, I have an example. The lower bound is 0 and the upper bound is 16. So that sketches out a rectangle from 0 to 16. Being uniform, it means that a range of values, now remember this is continuous, so they're not just spikes, right? There's a whole area here. So the probability denoted here, this is like the density curve for the distribution, and I can calculate this area, and it captures the probability of being between 0 and 4. So this looks similar, you know, to a normal distribution question, but this is a different kind of distribution defined by this uniform. So the chance of being between 0 and 4 will be the same as the chance being between 12 and 16. Okay? So I define variable x as the number of hours spent studying. So someone is as likely to study if their study hours are drawn from this distribution. So let's say student study hours are uniformly distributed, then a student is just as likely to study 4 hours as they are between 0 and 4 hours as they are to study between 12 and 16 hours. So it makes equal ranges of values equally likely. traces out a rectangle. So what you need to know about this is how you calculate areas, because areas will represent probabilities. Okay, this is the density curve. Even though it's a box, we call it a curve. So this is the density curve. As a density curve, the area under the curve should be 1. For a rectangle, area is calculated as the base times the height. That should be 1. The base is always upper minus lower for a uniform distribution. Still times the height. So now I can put the numbers in. 16 minus 0 is just 16 times height equals 1. So that means that the height must be, okay, so h must be 1 over 16. How does that help me? Well, now that I have the height of the whole box, I can figure out outcomes, probability of outcomes between 0 and 16 hours of studying. So if I was to calculate what this one was, the one that I laid out here, I would want this area, which is similarly just the base times the height, or height, I called it the width. The width is 4. The height is always 1/16. So you just multiply them and get 4/16 or 1/4. So there's 25% chance that a student studies between 0 and 4 hours, similarly between 12 and 16. So a student is just as likely to study a little bit as they are to study a lot. Okay. So I give you some exercises to practice that in different kinds of shapes. So this was the uniform, then I give you a triangular distribution as well for practice. So remember, for continuous distributions, it's always density with area, and we only calculate the probabilities between or on a range of values, not at a value, not like the discrete one. And here I just make a mention. The other two continuous distributions that you are expected to know in this class are the normal distributions, which we've already discussed, and the t-distributions, which we're going to talk about in Unit 6. Okay? So stay tuned for that. So now that I've done that, I'm going to ask you to try this problem while I get a glass of water. You guys can try this one. Five minutes. Are you done? What'd you get? You waiting for me? All right, so you're told x is uniform, -3 and 10. So that helps me draw it. So it's going to be a box between 3 and 10. And now what is the probability that x is greater than 5? So 5, let's say, is about here. How should it be 5? 0, 5. Okay, so let's say 5 is there. And so what I want to find out is the probability that x is greater than 5. So I want this area here. And then what is the probability that x is negative? Probability x is negative is, oh, that's what I did. I put 3 instead of -3. I knew I was, okay, let me draw this again. Sorry. It's easy for me to just erase. Let me just take that off. Okay, so this is now -3, not 3. -3, and I'll mark this as 0, and I'll mark this as 5. Is that okay? Sorry for confusion. Now, I want to get the probability that x is greater than 5. So that would be that shaded area. And the probability that x is negative, so that would be this shaded area. So this is not exactly to scale, but you get the idea. So let me just deal with that one first. So x is greater than 5 is equal to height times width. And height, well, what is the height? The height is what? Well, the entire area should be 1. The area is made up of the height times the width of the entire space, the entire density. So height times width. Width should be, remember I told you, upper minus lower. In this case, the lower is a -3, but don't lose that negative. That actually makes it turn into a positive. Right? This whole length here is 13. So that makes the height equal to 113. Good, you guys did good. 113. So finally, height would be 113, and the width of this area would be 5, so this is 5/13. And for the negative, what's the chance of being negative? That would be x less than 0. I'll put it over here. Again, height times width, but each time I'm using a different width. You guys got the hang of that? So the height is still 1/13, but the width now is 3. So it's 3/13. So I'm going to circle my final answer so you can see it. So that would be 3/13 and 5/13. Okay, so Gabrielle's confused with the subtraction. So remember, this is continuous, not, these are not discrete spikes or anything. So it turns out when I want the width is simply, it's simply this, upper minus lower. Upper is 10 minus minus 3, which is 13. Okay, Gabrielle? So yeah, if you want to turn these into decimals, 5/13 is like 38%. And 3/13 is 23%. Okay, good. Any questions? So that's how you deal with uniform distribution. Now there's other shapes, like I said, in the assignment, in the practice, and in the exams. There's other shapes. And you should be able to deal with them, given the instructions. Okay, so now I get to work on this practice assignment with you. Then I hope we're going to go to the Bayes rule, and then end up with rules of means and variances. Okay, so let's see. If you have no questions, I'm going to continue. Consider the following two boxes. These boxes contain balls with numbers. You will randomly select a numbered ball from the first box and then randomly select another numbered ball from the second box. The first question asks, given that the outcome of interest is the set of numbers on the two balls that are chosen from the two boxes, what is the sample space for this experiment? So what would that look like? So you have to think of all the combinations of the numbers in the first box with the numbers in the second box. So the best way to look at those is in a joint, in a matrix. A matrix. Make a matrix. So I'm going to place the ball numbers in the first box. I'm gonna make this bigger to do that. So box 1 and box 2 could be 1, 2, 3, or 4, right? So the outcomes could be 1 and 1. 1 on the first box and 2 on the second, 1 on the first and 3 on the second. So this is a way of writing the possible outcomes. And then 2, 1, 2, 2, 2, 3, 2, 4, 3, 1. Seems tedious, but it's worth it. You'll appreciate this exercise if you haven't already read it. Now what we like to be able to do is to recognize patterns, so we don't have to make these, handwritten things every time. We don't have to make lists or matrices. So these are the possible outcomes. There's 5 times 4, or 20 possible outcomes. Now, because there's equal chance of any of the numbers from the first box, and there's equal chance of obtaining any of the numbers from the second box, that makes these outcomes, these 20 outcomes, equally likely. So that means when you have equally likely outcomes, the probability of each one is the same, 1/20. So you could leave the matrix, or in the solutions for this practice assignment, it actually lists all the outcomes in curly brackets like this. Or how does it do it? Let's see. Let's see what they do. I think it's curly brackets. There it is. Yeah, so curly bracket. Oh, and they just write them as 1, 1, 1, 2, 1, 3, like that. Okay. So that's it. Those are the possible outcomes. So this would be satisfactory for me. Yes, 20 different combinations. Okay. Can I go to the second question? So just to say, the sample space S is equal to 1, 1, 1, 2, 1, 3, and you have to put them all down, right? Up to 5, 3, and 5, 4, with curly brackets. Okay, part B. I'm going to define now a variable x as the sum of the numbers on the 2 selected balls. So you pick one ball from here with a number and one ball from here with a number, and you add the numbers. The sum will be the outcome. Let me let you struggle with that a bit and see if you can, without cheating, without looking at the answers, what would your probability distribution look like? What's a probability distribution, right? That's this. The possible outcomes and their probabilities. Can we do that for this example? So I'm going to ask you now, is this distribution discrete or continuous for x? Before I leave you to try and make that for yourself. Is x discrete or continuous? Is it a discrete or continuous random variable? Anybody have the answer? It's discrete because I'm going to be able to write down all the possible outcomes. Means it's discrete. Okay? It's continuous when it's infinite possible outcomes. So, as you're thinking about that, what are the possible outcomes for x? So I write x equals x, so the variable takes on the value of x. What are the different x's? What are the possible sums? Right, so they could sum to, so what can help you in thinking about this is going back to the matrix and considering the different combinations. So here's a list of all the possible combinations. So what would be the sum? Well, this one would be 2. This one would be 3, 4, 5. This one would be 3, 4, 5, 6. And then 4, 5, 6, 7. You see? 5, 6, 7, 8. 6, 7, 8, 9. And that's it. And so those are the possible outcomes if I cared about the sum. But some are more likely than others. Which one is the most likely? Which is the sum that's the most likely sum? Six can happen 4 different ways. And 5 can happen 4 different ways. So maybe this is messy to look at. Let me redraw it for people who aren't getting it. But basically 5 and 6 are more likely than, let's say, 2 or 9. Okay, let me redraw this on its own little matrix so you can see all that. Let me take those off. All right. So first, let me just write this down here. So we realize that we're going to have sums between 2, 3, 4, 5, 6, 7, 8, 9. And I want all the probabilities for those. That's what a probability distribution is, right? It's the possible outcomes and their likelihood. So actually, you know what I'm going to do on this matrix? I'm just going to superimpose the number because I think it can work. So this would be 2, 3, 4, 5, 3. I'm going to go like this. 4, 5, 6, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8. 6, 7, 8, 9. I think you get the point, no? So what you see is there's 20 possible outcomes. Now, why did I do that? Because I don't want to draw the box again. It takes so much time. So there's 20 possible outcomes. And some are more likely than the others. Each one single outcome, right? Singular outcome has the same probability 1/20, but even though 2 has a 1 in 20 chance, 3 has a 2 in 20 chance, and 4 has a 3 in 20 chance, and 5 has a 4 in 20 chance, and 6 is the 4 in 20. Then it goes down again. 7 has a 3 in 20, 8 has a 2 in 20, and 9 has a 1 in 20 for a total of 120 over 20. You guys following this? So you can make those decimals if you like. If you don't like fractions, bear with me. Fractions are easier if you understand them, I guess, but if you don't, it can be confusing. You can change into decimals if you like, but basically that's it. Okay, so that's the answer. That's the probability distribution of x is the sum. Any questions? All right. So now we get to the fun stuff. I'm going to redraw the matrix. I'm going to redraw the matrix for the next exercise. That was nice. That went away. Okay, so part C. Part C defines events now. So it's going to combine certain outcomes. It's going to force you to use the distribution X, but combining certain outcomes, okay? So the first event is ball drawn from the first box has an even number. Ball drawn from the first box has an even number. So let's go back to the original thing, matrix. Ball drawn from the first box has an even number. So that happens here and here. So that's, I'll use the green for that. So the question was, find the probability of each of these events. So for A, what's the probability that the box drawn from the first box is an even number? Ball drawn from the first box is an even number. Thank you, Hector, for the percentages. Oops. So what's the probability of A? Right, so event A has the chance of 8 out of 20, which you can reduce to a percentage, if you like, of 40%. B is the event sum is odd. I'll use a different color for that. I'll use red. Sum is odd. So which one will give you an odd sum? Well, we have to remember back to the sum. So sum is odd would be 3. Let me make this big again. Sum is odd. So this would make that would be sum is odd, right? So remember that was 3 and 3. The next one would be 4. The next diagonal will be 5. Sum is odd. The next diagonal would be 7, where the sum is odd. And the last one is 9. Okay, so red denotes event B, the sum is odd. Everybody okay with that? What's the probability? Right, half of the time it's odd and half of the time it's even, so it's 10 out of 20. Good, Gabrielle. So that's 50%. And finally, the sum is 9. There's only one place where the sum is 9. I'll use black. That's here. So that was only in one place out of 20. So okay, we used the 20, the probability that any of those outcomes is possible is 1 out of 20. Any one of those pairs are chosen. But if we start looking at the sum, some of these sums are more likely than the others. And then I go and define these events. Okay, so there's a lot of things floating around here. I want to focus on the events, and I want to talk about their interrelationship. Now we can see them in their colors in the chart that I made, in the matrix that I made. I really like this exercise for the visual it offers. The next question is about the relationship between A, B, and C. What is the relationship between A and B? Do they ever overlap? Thank you, Hector. Do they ever overlap? Yes, they do overlap. Here, 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 here. Okay, so there are instances where outcomes are both in event A, or there are results that indicate event A and B has happened. You can have the first box being an even number and having a total sum that's odd. That can happen. And it happens in 4 places. Okay, so let's look at the question. Find A and B. So that's what we just did. A and C, we didn't do that yet. So let's work with A and B. Find A and B and determine whether each pair of events is disjoint, independent, or neither. So A and B, we determine that they overlap, so they are not disjoint. Being overlapping events, they could still be independent. How do we check if A and B are independent? What does independence mean again? It means if I know one event occurred, it doesn't change the probability of the other one occurring. So imagine that we are, you're remembering the probabilities, right? A had a probability, let's go back. What was probability of A? That's the green, right? So it was 8 out of 20. It was 40%. If you remember, it was A's probability was 40% and B's probability is 50%. Half of the time, the sum is odd. So notice A is 40% and B is 50% of the time. However, if I'm in A, the green, so ignore the rest, just these outcomes here. Out of the green circled ones, how many of them are A? So out of the ones, say I shouldn't have this, the green should stop here, right? So out of the ones that are A, how many of them are also B? Okay, so you guys are kind of, I'm not sure if you get it for sure, but okay, so what happens is the probability of B given A, that's what I'm asking you for. So if you're in the green area, what's the chance of being in B? Give me the probability. So if you're in the green, if you're in one of the green outcomes, what's the chance of being also a B outcome? If conditional, I'm in A, so I have to make it relative to A. I have to calculate things. So how many outcomes in A? There's 8 outcomes in A, so it has to be out of 8. So out of 8 outcomes, how many times are you in B as well? Four. Which is 50%. So you see, whether I'm in A or in the whole matrix, the chance of B stayed the same, 50%. So that demonstrates that A and B are independent because the probability of B happening did not change just because I was restricted to being in outcome A. Did you get it? So I really like this illustration because you can feel that, right? Because odd numbers and even numbers, that's 50-50 usually. So it doesn't even change. It doesn't change just because I restrict it to 2 rows of outcomes. So because B given A is the same as probability of B, it doesn't matter if A happened or not, it stays the same. That means A and B are independent. Now, how do you write that in a text situation to make it clear to me? Well, you could just write it like this. If you just show me this, probability of B given A is the same as probability of B. That's one way to show me. What about the other way around? What about probability of A given B? Let's try that. Let's make some Oh, I don't have any room. Interesting. Why don't I have any room? I'm perplexed. Okay. Let's try probability of A given B. What's the probability of A given B? So now B in the red. So you're in the red. You're in red. And out of the red, how many possible outcomes in the red? There are 4, 5, 6, 7. What am I doing? Yeah. 4. Right? 4, 5, 6, 7, 8, 9, 10. There's 10 possible outcomes. So conditioned on the 10 possible outcomes, what's the chance of being an A? So where does it overlap A? It overlaps A here, 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 and here. So that's 1, 2, 3, 4. So 4 out of 10. What's 4 out of 10? That's 40%. Isn't that the same as the probability of A? Yes. Since they're the same, A and B are independent. Okay? So that's all you have to show. The other way I was demonstrating, I'll just do one, I'll do that as well, but I think this is sufficient. The other way to demonstrate this is to write if you can show that this is true, okay, wait, let me put that. If you can show that this is true, then you've shown that A and B are independent. So the way I suggested that you do this is you take what's called the left-hand side, or LHS, and you find that. So what's probability of A and B? If you go back to the drawing, so where do they coincide out of the whole thing? Okay, so when I write that without a conditional, I go back to the whole matrix. So A and B happens 1, 2, 3, 4, right? Where they overlap. So it's 4 out of 20. Or 20%. Now what I have to do is check the right-hand side. I didn't leave enough room. Usually I like to do it over here, but okay, let's just do that. The right-hand side is equal to PA times PB, and just keep going. What's PA? PA was 40%, and PB was 50%, and 40% times 50% is 20%. Now, since the left-hand side is equal to the right-hand side, A and B must be independent. So what you've done is made a statement of independence and then proved it. Okay, so that's the second way of doing this. Okay. So take a screenshot so I can go back. And let's answer the last questions. What about A and C? A was the green, right? And C was just the outcome sum is 9. Do they ever overlap? No, right? They don't overlap. If we go back, the green and the black, let's see the drawing. Green and black, do they ever overlap? No, this is C over here, and this is A. So they never overlap, they're disjoint. So the probability is 0 for A and C. Maybe I should put notes here. Oh, we have to actually find the probabilities too, right? So let's do that. Right? A and B was 20%. I'll just put independent like that. Not A and B, but A and C. So A and B are independent, A and C disjoint. What about B and C? So B again is the red, it's the chance of an odd sum, and C is the chance of the sum being 9. So in other words, do the red and black do they overlap? Yes, they do. They overlap one time. Out of all the red, there's only one place where that happens. So it's 1 out of 20 is the probability. And then the question is, are they independent? I hope you know the answer here. Okay, so what am I saying? I'm saying that probability of B and C is 1 out of 20. There's only one place where that happens, that both B and C coincide. So are B and C independent? They're not disjoint because there is an intersection, so they do overlap. But the question is, are they independent? How do I check? So I can do the same thing I did right? They're not independent. This is neither. Why? Notice the probability of C is 120. But the probability of being C given B happens should be the same, right? But that's not the case. So let's see if I can write this. How can I write this? I'm going to make this bigger. A different color. Since the probability imagine that you're in B and you want to find C. What's the probability of C given B? Now you got to go to the subset of B and see how much of it is C. That is not going to equal to the probability of C. They should be the same if it was independent, but they're not. So let's go back. Let's look. Let's look at B. B is the red. The chance of, out of the B, right? Conditional means being side the red. It's 1 in 10. So it changed. Since it changed, being in B, the probability of C changes to 1/10. It's more likely than overall. So in fact, in terms of our diagrams, it would be the fifth diagram or the fifth case where you have all the possible outcomes of the Venn diagram and C is just one of them. Any questions? Am I blowing your mind? Review this video to understand this point. You know, you hear about independence in so many different ways. I think this is a really good example of showing you how, demonstrating how the subset, the result in the subset, the event in the subset, its probability should not change. It shouldn't be altered. It should be just as significant inside the subset as overall. Okay, questions? So that's all I want to do with that. You have a lot of other questions there to tackle. This was probably the more challenging one. The rest are straightforward. Just takes some time to work on. Okay. So now I want to go to Bayes' theorem. Bayes' rule. So in the spirit of conditional probabilities, Bayes' rule exploits this relationship. Remembering the probability of A NB is the probability of A times the probability of B given A. Okay, so this is the foundational definition of intersection. And we said if events are independent, then this conditional just becomes probability of B, and you just multiply them. But in general, this is what you get. We can exploit this let's say we knew something instead about B. Rather than A. Couldn't we write this in a different way? Couldn't this just as well be written as okay? So these are equivalent. I could write it either way. So this is very useful in statistics, where you might have some prior information and you can use it to determine the possibility of outcomes based on seeing events occurring. So here's an example. A lot of us have been looking at results, or we're watching cases mount in the news, cases of COVID or suspected COVID. And without getting into too many details, a test was conducted. Well, just because a test is conducted and a positive test result emerges doesn't necessarily mean you have the condition, whether that's COVID or other kinds of diseases. Diagnostic tests are not perfect. So it's really important to know the accuracy of the test. So here's an example, just demonstrating what this all means. You know, to live in this world, you really need to understand statistics. You really need to understand probabilities, because a lot of decisions are based on probabilities. And you're really limited if you don't understand what they mean. Okay, so 2% of the population has a particular disease, let's say. However, 3.2% of the population tests positive for the disease. Okay, so what's happened? The test is not accurate, right? It's too sensitive. In other words, a test for the disease is not perfectly accurate. From a population-based study on people with the disease, it was found that 75% of them tested positive. So, we know that from people with the disease, 75% had a positive test. So this is really important, that a baseline is established with a diagnostic test. You have to be able to really say that people have the disease to be able to actually test the diagnostic tool, the COVID test, for instance. Okay, so you'd actually have to know. So this is showing you that we know we have a group of people who actually have this disease. They've already been diagnosed, and now we're going to test them just to see how good this test is. So it turns out to be 75% tested positive. So this is mathematically in statistics. I really need to stress you have to understand the difference between intersection and conditional. Okay, so I've given you several exercises in the online quizzes to practice this. Practice, try and identify, which is and which is conditional. So I think it's pretty clear here, the way it says it. From a population-based study on people with the disease, it was found 75% of them. So again, the subset, people with the disease tested positive. Okay, so for obvious reasons, patients who suspect they have the disease need to know what is the chance that they have the disease if they have tested positive. So given this kind of a test that is inaccurate, it's not a perfect test, most tests aren't, what's the chance that a positive test means you have the disease? So I have this information, but I want this result. How can I find it? And this is where Bayes' rule comes in. I made a matrix below just to show you the different probabilities you're dealing with, okay? So this is an intersection. This is saying that the person has a disease and they test positive. That's different than the conditional concept here. What is the relationship? We know what that is, right? We know that this is equal to, from above, I want to focus on trying to write it like this, okay, with this conditional here. So I'm going to say that's going to be on the bottom, and probability that they have the disease and test positive. So that's the same as that. Right? It's conditional. It's like out of the subset, in other words. So that's why this divides it here. So do I have this information? Do I have the probability of having the disease and testing positive? Do I have the probability of having a positive test? No, I have this over here. Now, how can I incorporate that here? Well, I can also write this expression in terms of a conditional probability. I can rewrite this as probability of, and I want to do it the way I want it. Sorry. Where am I getting that from? From the definition of what and is, right? So we have up here the probability of A and B is just the probability, and I can write it two different ways as I explained, but I want to write it so that in this case, I'm saying the probability of A times the probability of B given A happened. And that's what I've done here. Maybe I'll put them in the other order so it looks the same. So you can see it. Why did I do that? I want to find this, but I use the reverse to find my answer, okay? This is a Bayes rule. Well, I've not completely expanded it, but this is going to get me there. So what do I have here? Do I have this information? Do I know what D plus is? Two percent of the population has a disease. So that is that. I have that. Do I have the second term? Yes, I have that here. So all I need is the probability of a positive test. Do I have that? Do I have that one? T plus. Anyone see where it is? Very good. So this is not hard. It just, you have to endure reading. I'm sorry, you know, it's in English if that makes it harder, but I guess it'd be more complicated if I was speaking in Spanish and reading this in English. So anyway, this is the best I got for you so far. Let's see. So I have these. I have all three. All right. So let's figure it out. So D plus, we know is 2%, 22%, sorry. The probability of testing positive if you have the disease, we're told, is 75%, and the probability of having a positive test is 0.32, and that's it. And now we're going to find out what's the probability if you have a positive test that you actually have the disease, and it's not 100%. So the chance it's like 50-50. It's 47% chance if you have a positive test for this particular disease that you actually have the disease. So that's not so great, is it? It's not a great test. Usually what happens is there's clinical diagnosis, not just a diagnostic test, right? They just observe symptoms to see if a person exhibits the common symptoms. And then they can see if they actually have the disease. Okay, so trying to do this with COVID is almost impossible because it's hard to find. I've never found these numbers. They're still working on it. But yeah, I wouldn't know about the tests, quality of the tests. It's very hard to find that information if it even exists. It's still in the making. Okay, so if someone has a positive test result, it doesn't necessarily mean they have the disease, but we take precautions, right? And we observe, put people in observation, isolation, and observe their symptoms. Okay, I wrote a lot of other stuff here, but you can read through that to get to the point. But in general, I wrote here the general expression for Bayes' rule, where I expand not only the top like I did in the last exercise, but you could also expand the bottom. If you didn't have information on A, so I always just, when I do this, I look here, right? This is a subset. So this is the same as this, but it can also be written like this. And I just described why you can do that to the top. What about the bottom? Well, the bottom is the probability of A. Now, A can happen so let's say you had no information on A, but you did have information on B and B not happening. So you could expand this. In fact, what is this here? A can be with B, and A can be happening without B. So adding those together would give me the probability of A. That's what this is doing. This is the probability of A and B, and this is probability of A and not B. And then I've summed them together. So it's very fancy. You know, you can do a lot using Bayes' rule, provided you have these prior probabilities or these conditional probabilities and the information you know of to get you there. Okay? So, any questions about this? So it's just using and reusing this relationship that probability of A and B is, in general, the probability of A times the probability of B given A, or it's equal to the probability of B times the probability of A given B. You can write it either way, and you can take advantage of that. So you guys should read through that. Try the exercises in the online quizzes, and let me know. Remember, you only have to get complete one quiz success. Well, I'm going to take your best mark on the quizzes for every unit, right? Or every section, not every unit, every section. There's 8 sections, and then I'm going to take 2 more top marks. So you have to complete a total of 10 and at least 1 in every unit to get the full marks for the online quizzes. So practice that. I don't have any more in the notes about diagnostic tests or in examples for conditional probabilities, but you have a lot of exercises in the online quizzes. Any questions? This is a really important thing here to see this. A can happen with B or A can happen without B. Total, summing those, would be the chance of A. I think it's really neat. Okay, that brings us to, it's 8 o'clock, and we are on rules of means and variances. Now this is a menacing set of notes the students find at the outset, but then I think, I'll do my best to make it easy. I think I can help. There's a lot to read here. Let's see, I want to start at the end just to show you that at the end, between pages 42 and the end, 42 and 49, see all these? These are just exercises that I want you to practice, because at the end, on the final exam, I'm going to ask you at least one of these, okay? Something similar to these problems. So they're all slightly different, and they all give you practice with the rules of means and variances. So you can count on that. That's an incentive. So 42 to 49, study those. Most of them have the answer, some of them don't. I'm going to start here. Let's solve this together, and hopefully this helps. Okay. Each year, employees of a large company receive a Christmas bonus of $500 plus $100 for every year they have worked for the company. Therefore, if X is the number of years an employee has worked, and Y, then Y is the Christmas bonus. So there you go. That's easy enough, right? That expression? Everybody's okay with that? So the ideas of the rules of mean and variances, is to take a distribution that we know about, X, the number of years an employee's worked, and translate it into a new variable that we don't know about. Well, because we know X, we actually do know about it. And I'll show you how, okay? So in terms of X, the mean duration of employment for employees of this company is 6.7 years, and the standard deviation is 2.4 years. Now, I haven't told you anything else about X, the number of years an employee has worked. I just told you about its mean, the mean, and the standard deviation. I told you about the mean and the standard deviation. So we've studied, we've kept this information, and Human Resources has this information, and it knows the mean and the standard deviation for the number of years of employment. I don't know the distribution. I just happen to know mean and standard deviation. But I don't know anything about Christmas bonus. Can I get information? Can I use this information on the employment to calculate mean and variance for this new variable? Well, yes, I can. It turns out that I'm going to write it like this. The expected value, or the mean, of Y would just be the mean of 500 plus 100x. So just think about it like this. If I was to take this distribution for X, let's just say just for illustration, let's say X looked like this. like a normal sign, some sort of symmetric distribution like that. And now if I took every value of x and I multiplied it by 100, what would happen to this distribution? So let's say there was a 0 here. Actually looks more like standard normal, right? So what would happen? How could you describe to me what happens to, what does 100 times x look like? So that would be, well, if I took every single value, 0 times 100, that would still be 0 here. And if I took 1 times 100, that would make it 100. So now what's going to happen? Oh my goodness, it's going to be really big, right? It's going to be like, the next one's going to be 100, and that makes that one negative 100. So it's really flat. It's going to be really spread out. It's just going to be this flat, spread out distribution. I want to make it more symmetric looking. Anyway, so you just imagine if I'm going to multiply every value, I'm going to spread it out more. So this creates a spread in the distribution. And what happens if now I add 500? What does a distribution 500 plus 100x look like? What would y look like? What would 100, so if 100x looks like that, what's 500 plus 100x going to look like? That means I would take each of these values and add 100 as 500 to them. So that one would become 500, and then the next one would be over here, it would be 600, and this one would have been 400. And so basically I'm going to shift, this distribution shifts over. Now this is very bad drawing that I'm doing because let me try this again, because what I'm trying to show you is getting lost on this. Let's do this. It's easier. I know I'm used to doing this in person. So let's say we have, this is x, and I'm going to multiply every single value like I was describing by 100. So that would make it flatter. So it'll just be flatter, more spread out, right? Still symmetric, but spread out. And now what I'm going to do, so that's going to be 100 times x. Now I'm going to add 500 plus 100 times x. And what is that going to look like? Oh, you can't see. So what's that going to look like? That's going to shift this entirely over. Where this one was at 0, this will shift this over. It'll look the same, but it's going to be 500 in the middle, etc. Okay? So what I wanted to demonstrate is that multiplying a random variable by a number spreads out the distribution by that number. If this number was less than 1, it would narrow the distribution. It would tighten the distribution. Adding a value shifts the distribution over on a number line. So what does that do to the mean? This, now back to the original question, what would that do to the mean? So the E means expected value. How did this factor change the mean? Whatever you do, so the rule is whatever you do to the variable, you do to the mean. So what ends up happening, if I did this to the variable, I'm also going to do it to the mean. The mean is just like one value, or it's amongst the values there on the distribution. So if I use that symbol for the mean, whatever I do, actually no, let me use this symbol and then I'll add the other symbol. So I could write it like this, or like, so whatever I do to x, I do to the mean. So what was the mean? $6.7. So actually, I probably should have written here throughout, because I was trying to do this in general, but for this example, it would be 6.7 would have been in the middle. And I'm not saying that the distribution looks like this. I'm just trying to make this as an example. And then this would have been still 6.7. Sorry, it would have been times 100, right? So this would have been 670. And then plus 100, 500, it would have been 1170. Okay, so I made it in general, but now you can see the numbers. Whatever I do to the variable, I do to the mean. So that's the result. These were in dollars because this is the Christmas bonus. So the average Christmas bonus will be $1,170. So if it was the mean of 6.7 and I multiplied every value by 100, the mean would also be multiplied by 100. And then if I was to shift every single value by 500, then I would also shift the mean by 500. Okay, so what happens to the standard deviation after that? What happens to the standard deviation? So the two effects one of multiplication and one of addition, which one affects the variance? Do both of them affect the variance? Did the variance change? Is it bigger or smaller? Right, because it's more spread out, it's bigger. Remember, the variance is the standard deviation squared. So it's flatter, so this is going to be much more variable. But the shifting didn't affect the variance, right? Only this part. So it turns out, in general, the variance of y is the same as the variance of 500 times x. However, this part, the scalar, the shift factor doesn't do anything. All that matters is the scalar multiplication, not the constant, not the shift. Now, how does it affect things? Remembering to do the variance, we multiplied the squared deviations from the mean. Right? So similarly, we have to square this term just like we square the deviations from the mean. So anything in front gets squared. Now, you're just asked for the standard deviation, and you're given information of the standard deviation. If I asked for the variance, this is what you would do. You would square the 100, and then you would have to square the standard deviation of 2.4. This would be the variance. Alternately, we can use the standard deviation. I can also write that as 100 squared, and the symbol would be sigma squared. So you see all the symbols. Those are all the same thing. So the answer for the variance it's really big, right? Because I squared everything. But I'm not asked for the variance, I'm asked for the standard deviation. So what you just want is sigma x, not sigma x squared. So that's the square root of that, which is small. Okay? So you could do that with the variance, or much easier, if you notice, what do you notice about this number? This is just 100 times 2.4, isn't it? So could we just do it like that? Yes, you can. You could have calculated standard deviation. But see, I don't write it like this usually. So again, the 500 just drops out, and this just becomes 100 times sigma x. Okay, so you can do it with the variance, which looks confusing, but it makes sense when you see the standard deviation result. So what am I doing with this notation? I'm just demonstrating that the standard deviation, the effect of the scalar, the multiplication, it affects the standard deviation just like it affected x. Okay? So, the mean of a transformation is the transformation of the mean. And the standard deviation of a transformation is just the scalar transformation of the original standard deviation. Okay, and I want you to, if you follow that visual up here, you understand why that happens. So with this exercise, well, let me get to the theory, but you should understand where I'm coming from. So those are the answers there. $1,170 is the new mean for the bonus, with a standard deviation of 240. Any questions? So the idea is knowing a variable's distribution, you don't have to, if you have a related variable, related as a linear transformation. What's a linear transformation? I'll get into that. If you have a related variable, related as a linear transformation or a linear combination, then you can just use these rules to find the new means and new variances or standard deviations of the new random variable that's related. So that avoids having to go through a lot of trouble to gather data, information, and delay or wait. So for instance, knowing about employment helped me know what what we should be expecting to pay out in terms of Christmas bonuses. That's really handy. Okay, I didn't have to know anything about the underlying distribution. Even though I drew a curve, a symmetric density curve, doesn't mean it was like that. I was just trying to demonstrate the logic about what we were doing. And there you go. Okay, so let's see. Oh, I guess I have some videos. Oh yeah, I have a long video on this and this is actually among the videos. Whenever you see this, it tells you that I made a video for this. I should probably just refer you to that because it's getting so late. Oh my goodness, 8:22. But maybe I'll just refer you guys to that. Shall I? And then next class, I think we can solve some of the, maybe we can solve some of the problems together. Yeah, I'm going to refer you to the video because it's already almost 8:30. I think I did a good job there. Okay, well, I'll just repeat myself. Let's see. I'll go until 8:45. Let's see if I can do 20 minutes. I can finish this. All right. So there's a lot to read here. I'm just going to skip over all the reading. That's for you to do. So we begin with means. Remembering that in the general case, now this is true for continuous or discrete distributions, but my examples, you see, are whenever you see a list, of outcomes and probabilities, that's a discrete distribution, all right? So my examples are in terms of discrete distribution because we don't assume you know calculus, but in calculus you should be able to do this for continuous distributions, having calculus skills, where you're actually calculating the area under the curve and integrating. So anyway, this is an example here that you can read about. So I refer to linear transformations of the mean. So this is what I just showed you. If a random variable x with mean mu x is adjusted by multiplying by the value b and adding a value a, then the mean is affected as follows. So this is called a linear transformation because this looks like a line, right? We multiply something and then we add. This is the slope and this is the y-intercept kind of thing. But anyway, that's called a linear transformation, even though I'm not going to talk about that as a line, but that's a linear transformation. And here I have below a proof demonstrating why it works. Now, I don't expect you to replicate this proof, but you can read through it and understand how it works in general. Or you can think about the example that I just gave you with the drawings, but this is the proof. Essentially, a mean is a weighted average for the discrete distribution. So I could distribute the probability to each of the terms of the linear transformation. And then I can split it up into two. So basically, you see, whatever I do to the value of x, I do to its mean. It's also a linear transformation of the mean. And that's what we just talked about. So that's the first result, and then there's some example of how to use that. Another thing about means is if you have two variables, and this is very important, this is really the most this is what makes the rules of means and variances very useful. What if you have two variables that you know something about, and you combine them into a new distribution? Now this is different, right? I'm going to do a sum of two variables. It turns out whatever I do to the variables, I also do to their mean. So their mean, the mean of the newly constructed variable from summing the two, that mean will just be the sum of the means. Similarly, the difference of the two variables will be the difference of the means. So you can think about this, the classic example, and I do give you an exercise to practice, is holding two assets, two securities in a portfolio where one is X and one is Y, and you have information on both of them, but holding them together will give you different outcomes, different expected, a different mean. And it turns out the mean of the new, of holding those two, will be the sum of the means. So if you think about a portfolio of assets, we're interested in the returns on those assets. The return on average will be the sum of the averages for the individual assets. Or if it's a difference, it's just the difference. Okay, so I'm repeating myself. I have some examples there. So, variances, this is the expression, remember, for variances, calculating the standard deviation, which is the square root of the variance. Variance is calculated as the squared deviation from the mean, but what I've done here is I've shown you the case for the weighted variance, which I derived and I solved some problems for in the GDS unit. And the reason I did it there is because it comes up in the theory and it's just easier to see this at this point. This should be familiar to you. Go back there if you didn't get to look at that, but this is the weighted variance formula. For discrete distribution. So what happens if we create a new variable, what happens to the variance of the new variable? So here again is a linear transformation. Notice we did talk about this, right? I said just ignore the a or the shift term. The variance is just becomes squared, just like all the deviations from the mean were squared, and then the sum was averaged, and then we take the square root to get the standard deviation. But before that, all the terms are squared, so that's similarly this shift term gets squared, and then all this is saying is that the variance of a linear transformation is a linear transformation of the variance, but no shift term, just the scalar multiplication. So I wrote that here, this is the variance, but this is the standard deviation, right? The square root, in other words. So those are those results. So I boxed off all the results you need. All the rest are just practice applying it. And we're almost done here. Here are the rules for two variables. So just like I added two variables and talked about the mean being the sum, the mean of the two variables is the sum of their means. What about the variances? Is the variance of the sum of two variables just the sum of the variances? Well, yes, only in a special case where the variables are independent. When there's no relationship between them. And I'll show you what I mean, what happens if there is a relationship. Similarly, but surprisingly, if you subtract two variables, outcomes, and you consider all the possible combinations of their outcomes, the variances are not subtracted, they're actually added. Why does that happen? Well, remember, we have to square all those terms off, right? So mathematically, we have to square all those deviations from the mean, and similarly that would affect the scalar term as well. That would end up being squared. So this -1 would also end up being squared, making it a positive. So you can think of it like that. You can also think about it that variance is just amplified, whether you're adding or subtracting the outcomes and thinking of all possible combinations. So that's, you got to keep that in mind, okay? So the variance of the sum of two variables and the variance of their difference is the sum of the variances, provided the variables are independent. That means if one occurs, it doesn't affect the probability distribution of the other, right? What if they do covary? What if they are not independent? What if they are affecting, they do correlate? Then there's an extra term. This extra term arises, and you notice here, it's a positive, and here it's a negative for the subtraction of two random variables. So I want to discuss why that happens. And notice here, all I have is x plus y, but I could have also a scalar term in front of those both, right? So what we're going to do, so you understand this better, is I'm going to introduce a matrix. Oops, I'm going to add a... So what we're going to do is take So I'm going to take the variable x, and I'm going to multiply it by a scalar. And I'm going to take the variable y and multiply it by a scalar. And then I'm going to consider them and how they correlate or covary. So I'm going to combine the covariance of ax with ax, the covariance of ax with by, the covariance of by with ax, and the covariance of by with by. What in the world is covariance again, right? Let's see. See if we remember what covariance is. So I'm going to use the covariance formula for simple that I showed you in the simple regression. So this is covariance of AX
with itself.
Couldn't I simplify this, taking out those A's? I'm going to take the A out here, and it's actually A squared, right? Because there's one A out of the first bracket and one A out of the second bracket, and that leaves me with this. Well, what is this? Oops. What is that term? Does anybody recognize this is the deviations from the mean? And it's squared. So isn't this just I'm going to use the notation. Isn't that what that is? So all I'm doing is I'm taking the variables, I've pre-multiplied them by a scalar, and I'm considering them in their correlation to each other. And I use the most general case of covariance. Covariance of AX with AX is just the variance of x squared, the variance of x times the scalar squared. So there you get to see, just using the simple or the sample result, you get to see that. It's less complicated than seeing it as a the weighted variance formula. Can you see all that? Oh no, things got separated. How did that happen? Can you see? Okay. All right, so that's, let me do it in a different color. So this is what I said. This is a squared sigma x squared. Then what's this one down here? This would be b squared sigma y squared, right? And what about these ones? Just looking for patterns here. You don't have to be a math genius. This is just looking for the pattern. So what would be what would happen here? Anybody can tell me? Oops. Okay, someone wrote something. So this would be this A and the B would come out, and then you would have the covariance of x, y. That's how you would write it. Okay, let's look at that together. So this would be right, that's what it would look like. And then you can see I would take an A out of here and a B out of here, and then it would leave the covariance term that's the covariance term. And we put that in symbols in Greek letters. So what I'm doing is I'm using the results that we worked with in regression just to show you, to demonstrate what it looks like, because it's just easier to look at. But then I'm using the notation in Greek letters telling you these are the results for the distribution, okay? For the population, in other words. Okay, so then the other one also, you guys agree that this will also be, even though it's BA, it's still the same as AB sigma x sigma y. So what we have here are two covariances, AB, and then the single one. So that's where the 2 comes from in those formulas that we just looked at. So what we found out, what I can say, how I can conclude with all this is the variance of x plus y would just be sigma squared x plus sigma squared y plus 2 covariance xy. Or I can make that, oh dear, I don't know. I have to figure out why my background is black. What we did was that's what we just did, but that looks messy. I was trying to make it look neat. Let me do it on the other page. So what I said was the variance of ax plus by is equal to a squared sigma x squared plus b squared sigma y squared plus 2ab sigma xy. That's the notation I used. You could also write it as cove. Which is what I do here. Okay? If they are subtracted, that's just a negative. Again, that happens because it's going to be the scalar in front of here, which is 1, times the scalar in front of here that's -1, that's going to make it a -2, right? I've also made these alternative expressions depending on what you're given. Remember that covariance is what? Covariance standardized gives you the correlation. So these notation, this is the correlation, but for the population. I could also write that as, I don't know, I have some contradiction because I keep on using anyway, let's see. I could write that as that, and that should be the same thing to you, okay? I like to write it like this because it reminds you of a simpler time. But I start using Greek letters, remember, when I'm talking about distributions representing population distributions. Okay, so if I had information on the correlation, I would use this formula. If I have information on the covariance, I use this formula. So these are just replications. These are just repeats. And this result is just says, just make the matrix. To find the variance of a sum of several random variables, you need to make the matrix and consider all the covariances and sum all of those together. That's what that says. And in the last statement, I mentioned, don't forget that the scalars in front come in front for the covariance, just like they would for the variance. So with that, you can do all the exercises while it's fresh in your mind. And I just missed by 5 minutes the end of the class. Okay, so you can watch the original video that I have, the edited one. I don't know, I don't think I edited. I think I just rambled. I just went through the notes. So I hope that helps. Try the exercises. You have, I think, most of the answers, and then next week I can go over any questions you have about it. Otherwise, I'm going to start Unit 5. Okay? We're supposed to have a test next week, I guess. But let's see. I think I can give you guys some more time for that test. I don't mind. But anyways, let's see. Let me see the schedule. Yeah, we can delay the test till the 7th. Sorry, the 5th, right? November 5th for the test. Okay, so then next week we can talk about any questions you have and do some exercises as well. And then, yeah, so we'll spend, what, an hour and a half the class on review, and then half the class on starting binomial. Any questions? Only 9 of you left. Hope the other ones can come back and watch the entire video and that it helps. Okay? So have a good week. Keep in touch. Let me know if you need anything. Take care. Enjoy the debates. Or the debate. There's only one debate. Yes, test 2 is units 3 and 4. Okay, thanks. Bye.
Take care. Good night.